this tutorial, I would like to again show you how to use Rat in combination with ParaView, and this time for the mesh calculation. So we just start with the simple mini toroid. That's basically the first model that is open once you start Rat. And I'm going to immediately go to the mesh calculation. And because it's always more interesting to add a bit of time dependence, we're going to add a powering circuit. There's two coils here, two coils, and one of them is in a toroid. This one has circuit ID 2, this one has circuit ID 1, and let's, for the sake of fun, for this toroid coil, which has circuit ID 1, let's make this into an AC coil. So we ramp it with a current to 1000 amps over a period of 1 second. The other one, the central solenoid, just making sure that it also has some nice large field. And also because mesh calculation has many parameters that it calculates, and it actually, in order to calculate, for instance, the temperature margin or the critical current margin, that kind of thing, it needs to have a material associated to it. So let's add like a cable. We add just here some standard Rutherford data that's available in Rat. So I right click on each coil, I say add material, and I select some LTS material, low temperature superconducting material. So now in the mesh calculation, we basically already made the circuit. So there's a time dependence for one set of coils, not for the other one. The other one is always powered. And if we then want to store the data for all the time steps, we need to go to the VTK settings of the mesh calculation. We first select the directory or the file that we want to store it in. So we need to have a folder actually here, because Rat will write multiple files for one calculation, especially if there's time dependence. And here I want to store time steps between 0 and 1 second. So I will have the full wave of current, and let's store like 25 time steps. So this doesn't take into account any induced currents from one coil into the other, right? Because Rat is still sort of a static calculation tool. But what it will do is at, for instance, time 0.5, it takes the current that it's supposed to have. So in this case, at 0.5 seconds, there will be no current in the toroid coils, so in these outside coils. And based on that, it calculates the magnetic field and all the other mesh calculation parameters. If I want to immediately store the data, in order to run the calculation, I click calc and write. And if I look into the logger, it will now go and do 25 times the mesh calculation. So for each time step, it will do one calculation, and it will write them immediately to this directory. So here you can name the directory whatever you want. If you click on this, you can select one, but you can also make a new one, like new data or something. If you say okay, you're immediately in this new file, but here we already selected to store the files in the ParaView data directory. Now, before I go to ParaView, I just want to mention it's an open source tool. So this is ParaView. When you open it, we use ParaView 5.13.3 for this tutorial. It's open source, and you can download it on the web. Maybe if I click here about, right. Yeah, it's probably, yeah. So if you go to paraview.org, you can go and download it there. It's for free, it's open source, and it's very good at data processing. Calculation has now finished. It shows up here in the processor as a finished process in green. And you can see in the logger that all these files have been written to your data folder. So this is your ParaView data, and that's basically where all these files ended up. And there's so many of them because each time step and each mesh, so our model here has like multiple meshes, because each of the coils that are in the toroid group and the solenoid have like a separate mesh. as you saw before. And the first thing, of course, we need to do is load our data. So I go, because I previously used ParaView in this directory, it immediately shows me this directory. And for ParaView, it writes multiple files. And for the plane calculation, which we saw in the previous tutorial, it were VTI files. But here for the mesh calculation, it writes VTU files. It's a slightly different format. It has to do with if it's 3D or 2D or something like that. But as always, if you have like multiple files in your data set, you need to select the .pvd file, so coilmesh.pvd, and open it, because that is where that's basically the main file, and it points to all the other files. Once you have opened it, it appears in the pipeline browser over here on the left. And for ParaView, every time you do an action, if you change something in the pipeline browser, you need to click apply. And once we do that, you see that our coils actually show up. And right now they're shown it to have different colors, because these colors basically represent the number, the mesh number. Each mesh is an individual object and it has a different number. You can change that here. So this is the properties box in ParaView, and that's where you can change the whatever you're plotting. And mesh calculation, as you know from Rat, can plot many different physics parameters on your meshes. The most standard one, of course, is the flux density. Let me quickly change the color here. So if I click on this hard with folder, I can change the color. And in fact, I'm gonna remove the opacity. I don't really like this color either. Let's go for rainbow. So now I'm plotting the magnetic flux density. By dragging this color bar, I can move it around on my screen. And you can see here, there are multiple time steps. So if I start at 0, in fact, we had this sine wave, right, in our circuit. So at 0, there's no current in the toroid coils, but the solenoid coil in the middle, that's always charged. So if I start at 0, you see there's almost no field on the toroid coils. There is a little bit because there's some field shine from the solenoid. The solenoid in the inside actually has some flux density on it, right? So there's about close to 2 Tesla, I would say 1.5 Tesla in the center. If I then continue in time, you see that actually the coils themselves, these also charge. And so they change color based on the magnetic flux density. Since we gave them superconducting properties in Rat, right, we added materials to them. So the superconducting properties of some Rutherford cable, LTS Rutherford, we can actually plot here, for instance, the temperature margin on the coils. There's quite a bit of margin on this coil, actually. That's not bad. That's good. We didn't charge it to too much. In fact, the temperature margin for the solenoid is 13 Kelvin. That's quite a lot. But okay, that depends on your settings, of course. And also that can be inspected as a function of time, just like for any other parameter in the list. So the electric field, everything that you would normally find in the post-processor of the mesh calculation. I'll quickly run the mesh calculation and have the post-processor appear. So everything that's normally showing up in the mesh calculation post-processor, which is this window over here. Sadly, I put it at time 0, right? So I just calculate one step here at time 0, but anything that's in this list is also in your ParaView data set as a function of time, because that's what we did in the calculate and write here. So by setting a time range, setting a number of time steps that's bigger than 1, we calculate and write the data as a function of time to ParaView data files. Now, what's next? Here, you can also basically, let's go back to the flux density, because for this coil, that basically says the most, I would say. It's the most clear example of data on this coil. And let's go to 0.25 seconds, because then that's the peak field, basically. You can extract data from just a single coil in here. And you do that by right-clicking on the coil mesh and adding a filter. And here I go to the alphabetical list of filters. A filter is basically a way of data processing in ParaView. And the first thing I want to do when I want to just select one coil is extract block. Because as we said before, these coils are, each one has a different block. And here in this properties list, you can then select one of them. I'll just select a random one. And then I click apply. And then it's actually executed. And you see this is the coil that we have selected from the list. And so we can now only look at the data for this coil, which could be interesting to you. It might be handy at some point. Let's put it in the middle of the screen. I use this button to center the view. Now that we have this single coil, if I right click on here, I can actually plot the data versus time, because I want to just know what all this, since I have this this charging and discharging, I want to see what it looks like in a graph format. So I right click on extract block, which is this thing, this extract block object is just a single coil. And from the list, I select the filter plot data over time. If I click on apply, ParaView will run over all the data steps in the data set, and it will calculate the average on the mesh. So the data here is plotted on the mesh. So on each point in this mesh, there is basically one data point. It will take the average, it will take the maximum versus time, it will take the minimum versus time, the median. Here you already see an example. But let's look at it a bit more clearly. So now that it's done, it shows up here. I'll open up a new view window. So this one's not gone. I can just switch between the two, and I chose a new one by using this plus. And then I get all these view options. And what I want to see is actually a line chart for my data set. And I now want to visualize by clicking on the eye on plot data over time, which is the only one that actually can be plotted as a line chart. And if I go and scroll in this properties list, now it already has selected here some properties which it plots. I will now unselect all of them because it's completely unclear what we're looking at. And just go and look at the average flux density. And that means that this will not be the peak, right? So it takes the average flux density on this coil. So it's not going to be 7 at the most, it's going to be the average at most, which is like 3.25. I can also look at the maximum. So if I scroll down in this list a little bit more, I get all these maxima for like force density, electric field, but also magnetic flux density, which is this one, what I wanted to look at. And here you actually see the maximum that you also see here in this coil. Now you can plot all these options basically. Just keep in mind that when it comes to vectors, so the flux density is a vector, it's a 3D vector. You can plot the flux density separately, right? You can plot x, y, z basically. So maybe x and y here are nice. I also had the average flux, no, the maximum flux density in the list is still on. There you go. So now I have the average flux density in x and y of this magnet versus time on the mesh. We can do that for a single coil, but we can also do this calculation for all the coils together. But since these coils are still in separate blocks, the first thing we need to do is merge the blocks. And then we can do the same calculation for all blocks together. So for all coils. So I clicked merge blocks and apply. And now there's just one single data object in this merge blocks data set. And again, I add a filter. It's now a recent thing. So I add plot data over time. And now it calculates the same thing as it calculated for this single coil that we had in the extract block. But now for the whole model that I have. So I can see the average flux density, the average current density, the average temperature margin, but also the maximum, the median, everything. It's calculating for everything that was in the model. Right, so plot versus data is finished. And I've opened it here in a new page again. And here, let's unselect everything. Right. And now let's look at the average current density, for instance. Now this is the average current density for all coils available in the model. So let's see, because there's one other thing that I'd like to show, and that is that you can manipulate this data as well by the calculator filter. You can also apply the calculator on a mesh. But also here, this is maybe a very intuitive way of showing you how the calculator works. So I right click here, I add the filter calculator, and then here in my properties list, I can change the name, neg current. A very simple example would be to show you the negative current of your average current density. Because for instance, you look here and you're like, oh, in red during the calculation, apparently I set a positive current, but I wanted to show it for a negative current, or vice versa. So then I go in this list and I select average current density from the list. Now it appears here in this box, and this is my calculator, and I can actually multiply it by something or do any other just normal calculation operation to it by using these things, or just plus, minus, and so on. And if I apply here, now it shows up as a calculator, and the data that's in there not only has all the data versus time that we just made, but the second thing in the data list is our negative current. And as you can see from here, we basically, this was the original, the average current, and by using a calculator, we made it into negative current. So that's quite handy. You can also, if you want to, for instance, have the force, you could, of course, the force density is in here as well, but you could use this calculator to multiply the current density with the flux density, and then you could get the force density. So that's another thing you could do it for. But you can do many calculations as long as you can always take any of these parameters from the list and do a calculation with the calculator object. Now, this plot doesn't look really nice, and I already showed it a little bit in the previous video on the plane calculation. But if we scroll down here in the properties list, we can actually change what the plot looks like. So here there's legend properties, chart title. So here we can say current density. We can change the font and the size of all these things. We can give the I scroll too fast. So we can give the left axis a title. I'm just typing this all, right? So now there is a left axis title, which I can change the font for. I can change the labels, the label size. I choose career, that's fine. You can make custom labels, which is nice, because for instance, now you can say 800, 400, right? And this way you get less labels than before. Minus 800. So if you don't want to have like a tick for every 100 amps per square millimeter, you can change that here. We can add a bottom axis title, and this is how you can actually make your plot look nicer. This line here indicates the time, and the time at the moment is what you set in here. So that's where the line goes, but you can hide it. So there's at the very top, below chart options, there's hide time marker. What would be nice, this time marker is nice if you make a movie. You can, for instance, split the screen, and here you can show the coil mesh again, the magnetic flux density, or whatever, magnetic field angle, something. And if I now click here, you have to click the thing you want to edit, right? So I click this one. I actually not hide the time marker. And now if I play, this is updated as function of time, although maybe angle was not the best one, but you see that the time marker also changes. So let's actually make it a bit more visible by doing the flux density and turning this thing. So if I play here now, you see this time marker moving while actually the flux density changes as well. And that's quite nice. You can save, again, you can save this as an animation, and then you will see this time marker in the animation as well. this is pretty much all I wanted to show you for the mesh calculation. I will also make another tutorial for data analysis in ParaView for a harmonics calculation, because what's nice there is you can plot the harmonics as a function of current, for example. So when you ramp up a coil, sometimes the field quality is something you want to know as a function of current, especially when you have an iron yoke, for instance, around your accelerator magnet. And that's what we'll discuss in the next video. Thank you for now, and see you in the next video.